Good afternoon. And my name is Leire Sanchez-Duenas. I come from the Surface Chemistry and Nanotechnology Department of Tekniker, and I'm going to present you my part of my PhD research on screen printing resistive temperature sensor development with sustainable carbon plastic. So first of all, who I came from, Tekniker is a research and development center located in the north of Spain in a village called Eibar. And it is a non-for-profit private foundation which has been applying the research for 42 years. We are specialized in manufacturing, and Tekniker's mission is to deliver growth and well-being to society via research, development, and innovation. We are almost 2,070 people, and we work in different research areas, such as advanced manufacturing, ICT for production, surface manufacturing, where this work is located on, or product engineering. So to have a context and a motivation of this work, I have to say that in the last years, the electronic demand has increased a lot because everybody uses electronic devices every day. So this linked with program obsolescence, it's implying a huge increase on the electronic waste diary. Most of the electronic devices that we use different materials such as plastics, or in this case metals, like gold, silver, palladium, which ensure the conductivity needed. Getting conductivity is up to 10 to 7 tenths per meter, but they also represent a high consumption of the called precious metals. So taking everything into account, we can say that there is a real need to develop more sustainable and environmentally friendly electronic systems. This could be done in different ways, such as selecting bio-based materials or biodegradable and recyclable materials, or combining these two strategies. All the electronic devices are used in different sectors, such as industrial sector, automotive sector, or energy sector, or others. And on all of them, we can find different solutions, like different types of sensors, heaters, and cleaners. But what this work is proposing is to develop temperature sensors with what I will explain now. We thought about developing sustainable functional basics by selecting bio-based materials and selecting properly the synthesis method and optimizing them. Then we decided to develop some resistive temperature sensor, because resistive temperature sensor modifies its resistance with temperature, and we could characterize them by the temperature coefficient resistance. And we decided to make wearable resistive temperature sensors by screen printing. And in this case, we will print the sensor onto fiberglass, because we have a certain application that it's what the substrate that it needs, and it's flexible also. So taking into account the composition of ink for screen printing, we can say that it is composed of 4 main materials. We have the functional material, which ensures the functionality of our ink, the binder, that could be the polymeric resin, and some solvents and additives that gives the ink proper capacities or properties. Selecting the material, all the materials, or some of them, in a good way, we could say that our ink is bio-based, biodegradable, or particle-free, or a combination of all of them. Normally, commercial inks were used for functional materials are metals like silver, gold, palladium, or so on, carbon nanoparticles that could be carbon nanotubes, carbon black, or another carbon particles, or conductive polymer as PEDOT-PSS. They usually use some resins, like epoxy resins, that are not as sustainable as we would like. So Tekniker's proposal is to use some bio-based materials that are bio-based. So we thought about using a PEDOT biopolymer, the water dispersion, that in this case is manufactured by the POLYMAT that is located in the University of the Basque Country, and they sent to us those dispersion. We will use carbon-based nanoparticles that some of them are also plant-based, so they are bio-based. And as binder, we will use two different types of binders. One base will be prepared with a natural origin epoxy resin and mixed with its hardener, that is a vanillin hardener. And the other one will be manufactured using fish rock gelatin. On the synthesis of these both inks, what we did was to first disperse the carbon nanotubes, in this case in NaButyl, because this is the solvent that is compatible with the epoxy resin. Then after dispersing it, we added the natural origin epoxy resin and its hardener, and by mechanical stirring, we get the paste that we could see on the image. The second ink was based by mixing porous carbon nanopowder that, as I have said, is plant-based, with the P.K Larrañaga dispersion provided by the POLYMAT, and after dispersing it, we added the fish source gelatin. Also, by mechanical stirring, we get the paste that we could see on the image. After this, we decided to make a rheological characterization, not only of these two pastes, but also of two commercial ones, one made of silver and another one made of carbon. As we could see in the image, the four pastes has a non-Newtonian behavior, so it's okay for printing them by screen printing. We also make the conductivity measurements, and it's true that Tekniker's developed inks do not have as much conductivity as commercial ones have, but this doesn't mean that they couldn't be used in our temperature sensors. The next step was to manufacture the sensors. We screen print the sensors into the glass fiber substrate. We glue them, and after that, to protect the sensor and avoid humidity effects, for example, we get them infused in an epoxy resin, as we can see on the screen, and we obtain all these sensors. After this, we characterize them in a climatic chamber, which modifies the temperature with a constant humidity, and we represent the variation of resistance with the temperature variation. For the commercial silver-based sensor, we could see that we have a linear tendency, and we can say that the temperature coefficient resistance that we are obtaining is similar to the one that we can find in literature. On the other hand, we have the commercial carbon-based sensor that we can see that the tendency is not as linear as the silver one, but we can approximate because the second order coefficient is small, so we can approximate. It's true that this temperature coefficient of resistance of this sensor is positive, and the carbon ones found in literature is negative. But this could be explained because all the components that are in the ink are contributing to the temperature coefficient resistance, so it could be possible. And then we characterize the both that we made on Tekniker. It's true that our results are not as precise as commercial one, but it's a logical result on development. But we can see that both has a modification on their resistance when changing the temperature. We will try to reduce next steps these unprecise points, but it's true that we can say that base B it behaves better than base A for temperature sensors. So, as a conclusion, we could say that we have developed a more sustainable paste for screen printing, and we have demonstrated its printability. That we have developed some temperature sensors, both with commercial inks and with the developed inks on Tekniker. And due to the used materials on the substrate, we can say that they are flexible sensors and could be used in different applications, such as wearable electronics. Of course, there will be more steps, and we will try to modify a little bit our formulation to achieve more stable results. We will try to implement these developed sensors on different applications that we are thinking about. And we will try to use the POSIT also for other type of applications. To end, I would like to acknowledge the two projects. One is the Swing project, that is a European funded project, and another one is the IDEA project, that is the Basque government funded project.